Hello. In the previous video, we introduced a discrete point of view or a discrete version of the world, which is appearing very often in applications. So when you have a function which you obtain from a measurement, it has a form of a discrete bunch of points. Or perhaps you were trying to solve a differential equation, an initial value problem, and you couldn't do it analytically, so you applied a Runge-Kutta method, and the outcome of a Runge-Kutta method is a bunch of points. So that's a practical view. On the other hand, the continuous point of view has many advantages. For instance, the calculus offers quite a few very powerful tools. So perhaps you want to use them. So we are wondering, okay, is it possible to somehow put a function through those points? And if I have a function through those points, then obviously I can use all those nice tools at my disposal. Another good question that people often ask in such a situation is, okay, I know my function at selected points, but sometimes I also need to know it somewhere in between. So what can I do? And again, the natural idea is to somehow fill in the blanks with some function. And this is called interpolation. Now, I don't have time to cover interpolation in this course. It's just an entry-level course with limited time. So I'm not going to cover it. I'm not going to make a lecture on interpolation now. And before you ask, it's not going to be on a test. But still, interpolation is fairly important, and it's a very interesting tale to share. So I'm going to just tell you a fairy tale about interpolation, so that when you hear somebody talking about it, you will know what that person is talking about actually. You will have some basic idea of what interpolation means. So here's the task. I have a bunch of data points, namely these ones. The picture is not good for that. Okay, here is a picture. So we have 1, 2, 3, 4 data points, and we would like to put some smooth curves through them, or perhaps not smooth, but a nice curve through them. When we think about functions and curves and expressions, the best type of a function is, of course, a polynomial, because with a polynomial you can differentiate easily, integrate easily, all kinds of things you can do easily with a polynomial. So what are the chances of putting a polynomial through some data points? And the answer is a very good chance, because in linear algebra we learn that if we have n+1 data points, then we can make a polynomial of degree n. Not always. We have to make sure that those data points have different x-coordinates. We cannot put 2 points like that and expect a polynomial passing through them. So that's definitely a bad idea. But if those points are reasonably given, like these ones, what's the x values? 2, 1, 0, -2. They are different. So if you have data points which satisfy this basic assumption, then you can put a polynomial of degree n through them. And actually, in linear algebra, they tell us that there is a unique polynomial like that, which is interesting. And perhaps I should be careful of degree at most n. Because if you take 5 points and you put them like that, you simply put a line through them. It's a polynomial of degree 1, which is at most 1, 2, 3, 4, at most 4. 5 points, degree at most 4. Okay? So that's the basic idea. It's a very simple idea. And that's one of the big advantages of this. Simple idea for a complicated problem. 1, 2, 3, 4 points. I have 4 points, which means I'm looking for a polynomial of degree 3 which passes through them. How do I get it? Well, let's first try a low-tech solution, a natural solution. Okay, common sense tells us if I'm looking for a polynomial of degree 3, then it looks like that. Now, what do I want from this polynomial? I want this polynomial to pass through these 4 points, which means if I substitute -2 into it, I get -5, and so on. So, I'm getting equations. How many? 1, 2, 3, 4 equations for 1, 2, 3, 4 coefficients. Wonderful. You can see how it all fits together. Okay, I'm substituting -2. A times -2 cubed plus b times -2 squared plus c times negative 2 plus d should be negative 5. And so on. I am not going to write all 4 of them because of course we are going to simplify immediately. Negative 8a plus 4b minus 2c plus d is negative 5. So far so good. Okay, the next point is 0. Oh, I love that. So 0a, 0b, 0c plus d is equal to 4. Okay, 1. A plus b plus c plus d should be 4. And finally, 2. 8a plus 4b plus 2c plus d is equal to 5. Here we go. What can I do with that? Well, let's see. Well, of course, in numerical analysis, I would simply change this into a system of linear equations, create a matrix, apply Gaussian elimination, and I will get a solution. And we will talk about it. There is a special lecture or a series of lectures exactly on solving huge systems of linear equations. But I don't feel like it today. So let's try to do some simplifications first. Okay, I'm going to take into account that d is 4. And I get a new system out of it. So, minus 8a plus 4b minus 2c is equal to minus 9. So far so good. Now I take the last one, 8a plus 4b plus 2c is equal to just 1. Okay, and now this one, a plus b plus c is equal to 4, just 0. Okay, how about if I take the first 2 equations and I add them? That looks like a good idea. If I add them, then a's cancel, c's cancel, I get 8b is equal to minus 8. So b is equal to negative 1. Very nice. Okay, what else? Let's see. b is negative 1. I feed it here. And I get that a plus c is equal to 1. So that's one equation that I'm interested in. It connects a and c. And I want to get another equation, and I get it from the first 2 when I subtract them. I take the second, and I subtract the first one. What do I get? I'm subtracting the first from the second. 16a, b's cancel, plus 4c is equal to, I'm subtracting 10. Okay, do I like it? Perhaps more or less yes. I take this equation, multiply it by 4 and subtract. And when I do it, 12a will be, I'm multiplying it by 4 and subtracting, and I get 6. A is equal to 1/2, c is equal to 1/2. So the polynomial I'm looking for is, where's a? Over there, over here. 1/2 x cubed minus x plus x squared, sorry, plus 1/2 x plus 4. That's the baby. Here we go. Did we need any theory for it? Not really. That was easy. Now, of course, if I had 50 points, I would be looking for a polynomial of degree 49 with 50 coefficients, and I would get a system of 50 equations with 50 unknowns. And I would feed it into a computer, and the computer would do it for me. Okay, so that's feasible. This looks like a good way to do things. Okay, here we go. That's the outcome. Now, what we see on the top, over here, is the polynomial as Maple thinks that it should look like. And we actually agree. That's nice. We agree on something. And here's a picture. A polynomial passing through 4 given points. Nice. Now, this could be the end of the section called polynomial interpolation, but it's not. Why? Well, because people were actually using it, and they were using it before the days of computers. Now, imagine you have 20 data points, and you are solving a system of 20 by 20. You wouldn't want to do it, I wouldn't want to do it, they didn't want to do it. So they were thinking, is there a better way to get this particular polynomial, because we know it's unique. So it's this polynomial, period. But can we get it in a different way, in an easier way? And here is an inspiration from linear algebra. When we have 4 data points, we are looking for polynomial of degree 3, at most 3, and polynomials of degree at most 3 form a linear space. And this linear space has a natural basis. And this natural basis looks like this. And just by taking linear combinations, we get all the polynomials of degree 3 or less. Here is an idea. Can we get a better basis? I'm going to call it L0, L1, L2, L3. These are polynomials of degree at most 3. When I say a better basis, what do I mean? Well, I have these requirements. Okay, I have those 4 polynomials. And when I substitute -2 into them, why -2? Well, that's the first data point I can see over there. X0, I'm going to call this one X0, and Y0, and this is X1, Y1, and so on, and this is X3, Y3. This fits with the degree of the polynomial. That's the customary way of denoting things. Okay, when I substitute -2, I want these outcomes. 1, 0, 0, 0. Why? Well, we are looking for polynomials. Polynomials which are composed using this basis. What does it mean? Well, I am taking these polynomials, multiplying them by numbers and summing up, making linear combinations. When I make a linear combination and then I put -2 into it, these 3 will not influence the outcome at all. So, of course, I'm interested in controlling what's happening at -2 because I want at -2 to have a certain value. And now, if I decide to have a basis like that, then I can control it just by working with L0. The other guys will not interfere at all. Now, here is the natural idea. Of course, I'm also interested in what's happening at 0. And I want this to happen. And so on. You can see the picture. At 1, I want to see the pattern 0, 0, 1, 0. And the last data, X3, is 2. Yes, 2. And there I want to see 0, 0, 0, 1. It's like an identity matrix. And now if I'm interested in a certain xi, let's say at 1, I always have a polynomial which will handle it, and the others will not interfere. This is very, very convenient. Now, assuming for a second that I have such a basis, how do I get my approximating polynomial? Well, very easily. My approximating polynomial will be just -5 times L0 x. Okay, let's put x here. And if I do it, then I already guarantee the value at -2. It's the right one. Then I will take 4 times polynomial L1 and 4 times polynomial L2 and finally 5 times polynomial L3. And you can easily check that this polynomial passes through all those points that are prescribed over here. For instance, if I take x equal to 1 and I put it here, then the first 2 will be 0, the last one is 0, and the value is just 4, exactly as I need it. So if I have such a basis, then creating polynomials that fit certain values is very easy. I just write a formula reading it from the data. So back to the key question. can I actually obtain polynomials like that? And the answer is yes, and it's actually quite simple. Let's see. I start with L0. Actually, I start with, I don't know, Q0. It's easy to force a polynomial to be 0 somewhere. Well, let's see. I need it to be 0 at the origin. I need it to be 0 at 1. And I need it to be 0 at 2. Here we go. That's a polynomial. I just wrote it like that. And it already satisfies the first 3 conditions that I have for the polynomial L0. Does it satisfy also the 4th one? That's a good question. Well, let's see. Let's check. Q0 at -2. How much is Q0 at -2? Well, it is -2 times -3 is 6 times -24. That's a lot. Let me check again. 4, 3, 2. Yeah? Looks like it. Okay. So it doesn't quite work, but this one does. L0x is -1 over 24 times x minus 0, x minus 1, x minus 2. That's it. That's how easy it is. Let's see. L1. This one should be 0 where? At -2. It should be 0 at 1. It should be 0 at 2. Okay. Since we are here at this pattern, let's finish the business. These should also be 0 at -2. And both should be 0 at 0. The L2, which is the 3rd one, should be 0 at 2. And this one should be 0 at 1. You can see that we always leave out one of the 4 expressions. Here we leave out the one with -2. Here we leave out the one with 0, with 1, with 2. Like a diagonal cancelling of factors. Now, what is the right constant here with L1? Well, what's the requirement? When I put 0, I should get 1. So I simply try to put 0 here, and I divide by the resulting number. I put 0 here, I get 2. 1, 2, it's 1/4. Here the requirement is about 1. So I put 1 here, 3, -3, so it's -1/3. And finally here, requirement is about 2. So I put 2 here, 4, 2 is 8. That's about it, 1 over 8. So I hope I didn't make any stupid numerical error here, but the important thing is the idea. And after all, this is not a lecture. This is just a fairy tale, and in fairy tale, things are happening which are not true. So, okay, let's imagine that these are the polynomials that we are looking for. Well, definitely they give 0 where I needed them, and I think this is okay, probably also okay. These are the 4 polynomials. That's my basis. You can see how easy it is. On a few lines, without too much thinking, I actually got the approximating polynomial. Did I really? Well, you take these formulas, you put them here, you multiply out. It takes, I don't know, 2 pages, and you find out that, yes, assuming that I didn't make a mistake here, you will get this polynomial, just written in a different way, in a very complicated way. But it works. These are called Lagrange polynomials, and this is called a Lagrange basis. Obviously, the Lagrange basis depends on those xi's, on the data points, on the x coordinates, but not on the y coordinates. We don't care about those. But the x coordinates actually appear here. That's the first important observation. So when you talk about the Lagrange basis, you need to know the xi's. They have to be different. And the second thing is that there is a pattern. So actually you can entrust this to a computer, for instance. Let's see. This first term, that should be L0, somewhere hidden there. So I see x, x minus 1, x minus 2. That fits. X, x minus 1, x minus 2. Then I'm dividing by 24 and multiplying by 5. Does it fit? That's a good question. I'm dividing by 24, multiplying it by 5, and there are 2 minuses. And there is no minus here, so that really fits, because no minus means 2 minuses. I can imagine them there. Then there is x plus 2, x minus 1, x minus 2. That's exactly this expression. I'm dividing it by 4 here, and then multiplying by 4 again. So that fits. How about the third one? I'm dividing by 3 and multiplying by 4. So I expect to see 4 over 3 with minus sign. Let's see, do I see 4 over 3 with minus sign? I do. And finally, I see 5 divided by 8. Oh, so I actually didn't make any mistake when I was deriving those polynomials. That's nice. Or Maple made the same mistake. That's another possibility. Okay, so that's the polynomial interpolation as it can be done through the Lagrange polynomials. This is a very useful notion. Let me put up some slide here. So we have numbers x0, x1, and so on. I actually sorted them by size, although it's not necessary. I create Lagrange basis polynomials using a formula. Now this capital Pi, that's a sign for product. So first let's have a look at this part, at the second pi. I'm multiplying factors x minus xj. That's exactly this part. And I'm skipping one of them. Which one? The ith one. So that's the diagonal. When I'm doing L0, I'm skipping the 0th term, and so on. When I'm doing L1, I'm skipping the first term. So that fits. And now I have to normalize it. I have to divide by a certain value. Now, that's a good thing. How did I get number 24 here? I took -2, and I substituted it for x. So I'm actually taking the same expression and dividing, just I'm putting -2 here. And I'm putting 1 here and dividing. And I'm putting, 0 here and dividing, and so on. So you can see that the formula is nicely symmetric. Here is x, and this will create the polynomials. And here is xi. That's the substitution which creates the right coefficient. So that's the Lagrange polynomials. And now if somebody gives me data, which also has the y values in it, I simply create first those Lagrange polynomials, and then I add them up with coefficients yi, and I have a interpolating polynomial. That's easy. A computer can do it, people can do it quite reasonably fast. So these are the famous Lagrange polynomials. And there are some good questions. First of all, is this polynomial interpolation any good? That's a good question. Let's have a look at some pictures. We have a polynomial, cubic polynomial passing through 4 points, and we are asking, is this cubic polynomial actually close to the function which is hidden by those points? Because recall that those points are measurements, for instance, or they could be coming from a solution of a differential, numerical solution of a differential equation. So there is a function hiding behind those points, and we created a new one. Is it close? And the answer is we don't know, because we don't know the original function, of course. So yeah, that's a good question. I mean, what if somebody decides to put a different curve through it? Let's say something which is based on exponentials or logarithms or something. So this interpolation is not a uniquely determined process. There's also a lot of decision-making coming in. We decided on polynomials because they are simple, but perhaps they are not the right object for this interpolation. So when somebody talks about interpolation, you have to keep in mind that there is nothing unique about this process, that by choosing one interpolating function, we are not saying that's the right one. It's just one of many possibilities. For instance, I could decide, okay, let's put a polynomial of degree 13 through those 5 points. And then I have many choices how to arrange it, and many different shapes passing through. And there will be also polynomials. So this interpolation, whether it's faithful or not, that's actually a question that cannot be decided. Which brings me to interesting notion. There is something called extrapolation. Extrapolation works like that. You get some measurements, and then you try to guess what happens afterwards. Well, now you know why extrapolation is important, because politicians are using it when they're predicting things. Ecologists are, and climatologists, everybody's predicting what's going to happen next. And they are basing it essentially on some past data. Now, there are many different ways in which you can extrapolate, but if you do it by putting a formula through those points, then this is a very chancy process, because I can choose a different kind of formula. Which one is right? We don't know. And that's why I'm not going to talk about extrapolation, because this can be easily something like a black magic. No, I am not going to talk about it. It's a different story if you create a mathematical model. Then perhaps there is some faithfulness, but it's another story. Okay, let's just talk about interpolation. I have a bunch of points. I put a polynomial through them, a very nice one, Lagrange polynomial. How far can I trust it? Yeah. There are some interesting theoretical results, and they essentially, many of them are like that. If you know the function, well, you don't know it, but if you know some properties, for instance, if you know that it has derivatives which are bounded by some number, then you can estimate the error that you make here in the middle. So theoretically, there are some answers, but you would have to know those derivatives. If you don't know them, anything can happen. The actual function may be going like that, you wouldn't know it. So that's a very good question. But still, polynomial approximation used a lot. We actually used it before. You have a bunch of points which are coming from a function. We sampled it. And we want to integrate. One obvious idea is that we put a polynomial through them and we integrate. That's one of the valid methods for integration, for numerical integration. So this is really a popular field, putting a polynomial through points, and people get fairly optimistic about it based on examples. For instance, this one. Here is a function. It's x times e to negative x. That's actually a popular function in calculus classes, sketching the graph. And what I did here is I sampled it at 5 places. So n is equal to 4, n is the number of divisions, and n plus 1 is the number of points. We can see them as black circles. So one circle here, one circle here, one circle here, and so on. And then I asked Maple to put a polynomial through those 5 points. So it will be a polynomial of degree 4. And I didn't specify whether it should be in the Lagrange form or not, because it's actually the same polynomial, and I don't care how it looks like now. So that's the red curve. The red curve is a polynomial, and it's not really a good match. So what I'm going to do, I'm going to put more points in it. Let's say 6. Plus 1 is 7. So there is 6 segments and 7 points. And now it looks much better. And let's try, let's say 8. So 9 points. And that's a perfect match, essentially. So this example makes us very optimistic. And you can try this with many functions, cosine, sine, logarithm, exponential, whatever, and you will be getting good matches. So people got really, really optimistic about polynomial interpolation. It really seems to work well. However, then a guy called Runge got an interesting idea. He took a function 1 over 25x squared plus 1. That's a nice, simple function. It's a bell curve. Not the Gaussian bell curve, but it's another bell curve. It looks very nice. And let's try to run the same question again. So let's see. 5 points. Well, that's too much, as expected. So how about 8 points? That's better. Well, is it? What's happening at the endpoints? How about if we try 10? What happens if we try 13? What happens if we try 23? That's my second most favorite number. Wow. So what you can see is this. There is oscillation happening at the endpoints. And when you get more and more and more points, then the amplitude of the oscillation is actually increasing. Now we are going all the way to almost 40. If I use 32 points, or 32 segments, 33 points. Wow, this got really bad. And what's happening here? The situation is supposed to be symmetric because, I mean, the function is symmetric, the points are symmetric. What we see here on the right is actually the numerical errors because the powers are so high, x to 33 and so on. The numerical errors got totally out of hand. We should rather trust this part on the left. And it looks like something like 7,000. Okay, so we are trying to approximate let me remind you, we are trying to approximate a function which goes between 0 and 1, and we got oscillation which is almost 10,000 tall. This is called Runge phenomenon, and it simply happens. This is the unpleasant habit of polynomials to oscillate. Polynomials of high degree, they like to oscillate a lot, and this is a problem. So the polynomial interpolation, it is used, but not as much as people would like to, because they are aware of this problem. And well, there is not very much you can do about it as long as you stick with polynomials of high degrees. So this was a nice idea. The Lagrange polynomials, they are used. This is not a blind alley or anything like that, but one has to be very, very careful about it. So we will now try to find or to come up with a different idea which avoids this problem. Now, of course, you could try different type of a function. You might say, okay, can I put something which is based on exponentials through, or sine cosine? And you can try such interpolation, but it will be much more complicated to obtain those formulas than this. So what people did, they like to stick with polynomials, but they limit the degree. Now, is it possible to limit the degree if you have 50 points? How do you get a polynomial of low degree through 50 points? That's impossible. And there is a very simple idea. Let's make room for it. Okay, here is the situation. We have n+1 data points. And of course, we assume that the xi's are distinct to avoid trouble. Now, we can put a polynomial of degree n through them, but we do not want that because n is too high now. However, here is a trick. When we have n+1 points, and we can order them to go one after another, they actually create n segments in a natural way. For instance, when I go back to my example, it looks somehow like that. 4 points, and therefore there are 3 segments. And for each of them, I may decide to use a polynomial of certain degree. Now, because I'm connecting just 2 points, I am not forced to go to high degree of a polynomial. For instance, if I want to make it simple, I just use polynomial of degree 1 for each segment, which means a straight line. And I get a function which interpolates, and it's not too complicated in some way, because the polynomials are very simple. It will be given by cases. It's a piecewise defined function. And the first piece, let's say, is here. Okay, let's see, 2. So the basic value is 4. And then I have to use the right ratio. So it's 9 plus 9 over 2x. And this formula is valid on the interval -2, 0. That should be it. Okay, the next segment. That's just a constant function 4, and this is valid for x between 0 and 1. Now you can notice this is not entirely correct from formal point of view, because 0 belongs to both alternatives. Properly, I should make one of those brackets rounded. But actually, the whole idea is that these 2 formulas, they connect. They join here, they meet there. So I can afford to put 0 at both places. And likewise, here x will be going from 1 to 2. And the formula is based on the point 1, which is here. So the basic elevation is 4. And then I'm going by 1 and by 1. So it just plugs x minus 1. So these are 3 linear formulas that interpolate, when I put them together like that, interpolate my 4 points. That was simple. And this is a spline. What is a spline? Well, there are several meanings of the word, depending who you ask. And the most general meaning that I can think of is this. A spline function is a function which is defined piecewise using polynomials. And those polynomials, they join at those meeting points. In other words, I can say simply that this function is continuous. That's what it means. Those polynomials, they have to follow nicely. A continuous function composed of polynomials. That's a spline in general. Now, this is actually a linear spline because I'm using linear functions. And when I'm using them to interpolate, there is a second requirement that the values should match at those meeting points. They should match with the data. Other than that, this is very simple, a very nice idea which is actually used in applications. For instance, in many programs, if you ask the program to plot a graph, they do exactly this. They sample the function which you supply, and they connect those points with straight lines. And that's what Maple does over here. It looks like we are going using some curves, but in fact, these are just little straight segments in this picture. So this is a very popular thing. On the other hand, it has some disadvantages. The major disadvantage is that we have sharp bends here, kinks if you want, which means that there is no derivative there. So the idea is that people actually use more, perhaps, to use polynomials of higher degree so that you can make those corners round and you will get a nice smooth shape. Well, this was degree 1. What if we try degree 2? That's a good question. There will be a polynomial, let's call it P1 here, polynomial P2 here, and polynomial P3 here. You can notice you have n plus 1 points, which means n segments, which means n polynomials. And you can call them P1 through Pn. It fits nicely. Okay, how do they look like? They are supposed to be quadratic. So this will be a1 x squared plus b1 plus c1. This will be a2 x squared plus b2x plus c2. Oh, there's x missing here. And there will be a3 x squared plus b3x plus c3. 1, 2, 3, 4, 5, 6, 7, 8, 9 variables. In general, if you have n plus 1 points, then there will be n times 3 unknowns. If you want a degree equal to 2. Now, how many equations do we have? That's a good question. The polynomial P1 has to be anchored to these 2 data points. So that's 2 conditions. And the same will be true for each polynomial. So there will be 2 n conditions coming from the anchors. Which is not enough, obviously. There is a imbalance there. So let's ask another question. Okay, we have polynomials of degree 2, which means that they are curving. And what we really want, and that was our inspiration, that there is a nice smooth transition over here. So we want the derivative here to exist, which means that we ask for the derivative of the first polynomial and the derivative of the second polynomial to agree over here. It will be one-sided derivatives. But since polynomials are continuous and differentiable and so on everywhere, I will just talk about derivatives, not one-sided derivatives. So the derivative of P1 at this second point, which is 0, should match the derivative of P2 at the same point. That's one requirement. We get the same requirement here. P2 derivative at 1 should match P3 derivative at 1. And that's it. There are no more matching points. So, how many conditions do we get? That's a good question. We have n plus 1 points in general, which means n segments. N segments, n polynomials. But when you have n segments, there is just n minus 1 meeting points. N minus 1 conditions on derivative. And now you make a little inventory and you see that there is one condition missing. Which is not a problem. It means that you have some flexibility, you can adjust. But the problem is that in applications you do not find a reasonable 3nth condition that you could apply and it would work well, consistently, do things that you want. So for quadratic polynomials, determining which one to use is not obvious and it doesn't work quite well. And that's why people do not use splines of degree 2. There is more trouble than the advantage. Well, advantage is that it's simple. You just get, few coefficients. Parabolas are nice. But this is not good enough. So what people do, they mostly go for degree 3. Cubic splines, it's called. And that's another meaning of the word spline. When people say splines, they actually mean very often cubic splines. So let's make some inventory here. Let's say that we ask for the degrees to be 3. We have n plus 1 points, n segments, n cubic polynomials. Each cubic polynomial has 4 coefficients. So we get 4n coefficients. What are the requirements? Well, we have those anchors. 2n anchors. Second, we have high-order polynomials. They are curving. So we can ask for the derivative to exist also at those meeting points. Nice, smooth transitions. So, how many conditions? n minus 1. n minus 1 conditions on the first derivative. Which is not nearly enough, but we have polynomials of degree 3, so we can also ask for the second derivative to be nice. Because the fact that the first derivative is nice can still mean that at this point, at the meeting point, the second derivative, the curvature, changes sharply. And this can be also unpleasant. In engineering, we usually care about the first 2 derivatives. Those are the most important ones. So it's nice that we can actually ask for the second derivative to be continuous. So we can say this whole thing like that. We are interested in a function which is defined piecewise using cubic polynomials, which is continuous, has a first derivative continuous, second derivative continuous, and fits the data. And now, when we look at it, we sum it up, we get 4n minus 2 conditions, which is too short. So we have an opportunity to ask for something. And unlike the case for the quadratic splines, for the cubic splines there are some interesting ideas. Here is one. It's called natural. Natural conditions. Natural conditions simply ask that the resulting spline does not curve at the endpoints. So the first polynomial at the first point, which is x0, the second derivative should be 0. The first segment starts flat. The last segment, Pn, should end in a flat way as well. This is used very often, and it really works well. It performs quite nicely. The second thing which is used perhaps less often, it's clamped condition or conditions. And it goes like that. You look at the first function that you are having in your spline, you look at the derivative and you say it should be d1. And with the last function, the derivative at the end should be d2. What's d1 and d2? Well, this comes from applications because most people don't do interpolation just for fun. They are trying to solve some real-life problem. And from the real-life problem, there may be a requirement that the spline should start and stop at a certain rate. It should have a certain slope. You clamp your spline to those directions. And that's the conditions. That's clamped conditions. Here is another one. Periodic condition. This makes sense if the first and the last values actually agree in the data. Because then you can imagine that it goes on in a periodic fashion. And this makes sometimes sense in applications. So then it would also make sense to ask that the first derivatives and the second derivatives are periodic, that they follow nicely, they match at the endpoints. So the first derivative of the first segment at the first point, so we are at the left end, should match the derivative at the opposite end. And the same goes with the second derivative. So these are probably the most popular types of conditions that you can impose on your cubic splines. And that's it. That's how simple it is. So these are just a bunch of conditions that you have to solve, probably using linear algebra approaches, elimination or something. But there are also more efficient procedures made for it because the cubic splines, they are very, very popular. They are used in many applications. For instance, they are used in solving differential equations even. But I'm talking about more advanced methods now for partial differential equations. You can also meet cubic splines in computer science, for instance. in design, in graphical design, when people form shapes, cubic splines are very popular. You can actually meet them when you are sending things to a printer, because most likely the printer works using splines. The shape of each letter is composed of curves, and when you send the data to the printer, you are not sending the precise shape. You are just sending a few points, and the printer uses splines to interpolate and to get the actual shape of the picture, or of the letter. So cubic splines are very important, and there are procedures prepared for them so that you don't have to really solve manually or by computer in a primitive way some systems of equations. This has been streamlined, and it works really nicely. Let's have a look. I have a function here which is x by e to negative x. That's the hump for which we used polynomial interpolation before, and it worked quite well. So let's see how the splines look like. These are the splines of order 1 straight lines. That's how the graph is actually constructed. And if I increase the number of the points, we get a reasonable match. Well, let's try something big, like 101. Here we go. We get a perfect match. That's actually how the graph was drawn, more or less. So perhaps 51 would be better. Here we go. Occasionally, I see a little bit of red, a few pixels of red in the hill, in the peak. Okay, let's go back to 8 as a number of division points. That's how we started with those linear splines. And now I'm going to ask for spline of degree 2, which is not very good, but it works better. Now, how did those splines start? There was one condition missing. Well, Maple has some ways, and it decided to use a certain condition, which I didn't tell it to do. It just chose one. And you can see that there is a big problem at the beginning. Yeah, not very nice. So let's go directly to spline of degree 3. Here we go. That's a cubic spline. Things at the left end point are much better now. And if we go to, let's say, 16 or 13, that's my favorite number. 13, yeah, we are getting, wow. Here on the right, the match is almost perfect. Just on the left, it needs a little bit more work. But this is not surprising because there is just 1, 2 points, 3 points, let's say, on the left. So I increase the number of samples. Here we go. For 23 samples, almost a perfect match. Cubic spline. Wonderful. Now we will try and apply the cubic splines to the 4 pieces of data that we have over here. And what we see here is 2 curves. The red curve, that's the cubic polynomial which we derived at the start of this lecture. And the blue curve, that's the cubic spline. Which one is better? And that's exactly the point I was talking about earlier. We don't know. Because we do not know the data behind those 4 points. So here we have 2 possible interpolations. Which one is right, we don't know. And now the question is, if you want to extrapolate, if you want to know what happens next, you can use these 2 different curves and you will get different answers. So, yeah. Anyway, that's it. Let's look at the slide, because the cubic splines are very useful, so I prepared one. We have a bunch of data points, and I ordered them, so the xi's go one after another. And we have a cubic interpolation spline, which is a twice continuously differentiable function. That was the short way to express those conditions. But we can also see them here. Instead of just writing them, they are done in a precise way. So we have polynomials on the interval xi minus 1 xi. They're called pi's, just like we did over here. Each polynomial is of degree 3. It's a cubic polynomial. The first condition says that each polynomial must match the data points at the endpoints. So pi at xi minus 1, that's the left end. Pi xi, that's the right end. They should match the values yi and so on. The second condition is this one. We are comparing the derivatives of the 2 successive polynomials, pi plus 1, at meeting points. And the third condition is about the second derivative. That's it. So this slide sums up the substance of cubic splines, a very useful tool for interpolation. But we did not really cover anything. This is just a fairy tale. So let's finish it with a few more fairy tales, quick ones, short ones. people had some other ideas. For instance, if I go back to our, if I go back to our Runge problem, Runge phenomenon, imagine that you have a function and you know it, and you want to integrate, but you don't know how to integrate. So what you do? You sample, and you can put a polynomial through it and integrate a polynomial. We talked about it, and there is this Runge phenomenon. One possible way to alleviate Runge phenomenon is to choose the points in such a way that they are not equidistant, but you put more of them as you reach the ends. And it turns out that if you do it smartly, then the Runge phenomenon does not happen. So there is a special way to choose the points in your partition in such a way that polynomial interpolation works well. But the selection of points is rather complicated. It's not like a nice formula. It's really complicated. It requires some knowledge of really advanced theory. So this is really just a fairy tale. Anyway, if you do that and you integrate your polynomial, Pn, you get a method of integration, of numerical integration, which is called Gauss integration. So this is one interesting thing, that you can improve if you have a power over the points, over the partition. Generally, it pays to put a denser partitions if you know that you have some troublesome places with your function. So for instance, if your function goes like that, then it makes sense to put a sparse partition over here, but a very dense partition over here. And then your interpolation will work better. Even if you try the cubic splines, they will be better. So that's one thing I wanted to talk about. And the second one is like this. You have a bunch of points. You want to interpolate, perhaps, or perhaps not. That's a good question. You just want to capture the essence. Because if those points come from some measurement, then most likely they are not correct. Each of them perhaps carries a small error of measurement with it. So it doesn't really make much sense to ask for a strict interpolation. Instead, you may sort of see some tolerance around those points, and you can ask, is there a nice curve which would pass through these gates and have some nice properties, for instance, a polynomial? Or, since you are talking like that, you may even ask for, let's say, an exponential if you have a suspicion that there is an exponential happening here. So that's one interesting kind of almost interpolation, and there is a special mathematical theory about it. And if you are curious, you can read about it. You can simply drop this assumption that you know the size of the gates. Perhaps you don't know it. You just know that there is some uncertainty, and you can simply ask for a curve of specific type which matches your picture in the best possible way. This could be an exponential or a logarithmic curve. You can ask for hyperbola, all kinds of curves. If you have a reason to suspect that some curve is a good match for the situation, then you can try to match this. Okay, this one is better. You can try to match it in the best possible way, and what you get is, for instance, the least square method. So again, this opens the door to another interesting area of mathematics. So all this is hidden under the umbrella of just getting some pieces of data, some data points, and trying to put a function through them or around them in the best possible way. That's a very interesting and important field of mathematics, of numerical mathematics, and there are lots of interesting ideas and procedures hiding there. And I just outlined the basics which are somehow related to what we do here. And that's about it. See you next time.